Hello, welcome back to everybody's favorite video series, Watch Your Professor Grade. So, our first problem today, let f be a function from the open interval a, b to the reals such that f is differentiable on the entire open interval a, b, and such that the derivative of f on this interval is bounded. So we're looking at the range of the derivative, and we assume that the range is bounded. Prove that f is uniformly continuous on the open interval ab. Ooh, this is cool because I believe of all the people who I've graded for this assignment, this is the first person to choose this problem. So that's wonderful. All right, let's see what we got. Since f is differentiable on AB and f prime is bounded, okay, for a epsilon greater than 0. Okay, so we don't need to put the in there. There exists, okay, so using the symbol, this violates, it's almost right next to it, number 20 on here, right? So in formal proofwriting, we're not going to be using these sort of symbols that there exists, the for all, arrow for implies, or even the double arrow for implies. So this is number 20 on our list of homework issues. So we just write it in words, all right? For epsilon greater than 0, there exists delta of epsilon greater than 0 such that for all xy in AB, where x does not equal y. All right, so this is fine. However, you can actually shorten it by just putting the not equal to in between them. All right, and then you don't need to have this expression. Okay, then you have absolute value of x minus y is less than delta. Okay, there's a couple things going on here. One, before you would write this down, you need some sort of words, right? So we believe this is number 13 on our list. We avoid starting sentences or new clauses within a sentence with math symbols. So after the comma, we don't want to start immediately with math symbols. Okay, so there's a little 13 error here. But there's something more. Let's read this sentence carefully. Since f is differentiable and f prime is bounded, for epsilon greater than 0, there exists a delta of epsilon greater than 0, such that for all x not equal to y in AB, difference between x and y is less than delta. So I think you're probably setting up the next sentence where you're saying, therefore, the distance between f of x and f of y is less than epsilon. But that's not what you're saying. You're actually saying that there exists a delta such that x and y are within delta. Now, besides the fact that you wrote here delta of epsilon and here just delta, that's its own problematic part, right? So you'd want to call this delta of epsilon also. The point is, there's no question that I can find 2 points that are within delta of epsilon of each other, all right? That's what this sentence says, though, that you're concluding, is that you can find x and y that are within delta of epsilon. What you want to be saying is that you can find points within delta of each other, and if you can find points within delta, then the difference between f of x and f of y is less than epsilon. Okay, so then that really needs to be justified. And you're saying somehow because f is differentiable and f prime is bounded, but we don't have any sort of result, right, that says if you're differentiable and bounded, then this happens. In fact, this happens. What is this? Well, this is exactly the uniform continuity condition, and you're just claiming that it holds. Okay, what we do have, though, is problem 7 from homework 5. So let me reproduce that here. So problem 7 from homework 5 said if you had some function with domain D, and you had some positive real number m such that for any 2 points in the domain that were different, then the absolute value of the difference quotient based at a was bounded by m. And if you had this condition, then f is uniformly continuous. Okay, at the time we did this, I talked about how there's actually a name for this condition. This is actually called Lipschitz continuity. All right, so a function which is Lipschitz continuous is uniformly continuous. So that's actually the connection here. All right, so if we can show that the difference quotient is bounded by some positive constant, then we're done. Well, where are we going to get some positive constant to bound the difference quotient? Well, my goodness, look at this. We're told that the image of the derivative is bounded. That could be quite useful here, right? So we know that the image of the derivative on the interval AB is less than or equal to m for some positive real number. Well, it could be 0, right? Okay, so maybe that's a special case. So let's write m here greater than or equal to 0, right? And what's going to happen if m equals 0? What would that mean? That would mean that the derivative is 0 all along AB. And we have from another problem that if the derivative is 0 for all points in your open interval AB, then this function is constant. So this implies f is constant, and of course a constant function is uniformly continuous. Okay, so the m equals 0 case, not a problem. So we can assume, right, assume m is actually positive. Okay, now I look back to your proof again, and let's put the issues back up. You're starting this next sentence with then, which we'll just note, right? We're not supposed to be doing that. Okay, we don't let if or suppose. Oh no, sorry, this one. 8, avoid since then. Only use then after an if, right? So we're not starting our sentences with then. Okay, but the important part here is that you're trying to use the mean value theorem. Okay, well, again, doing this. All right. What does the mean value theorem require from us? All right. There were two hypotheses in the mean value theorem. You had to be continuous on a closed interval and then differentiable on the open interval. And you notice we have differentiable on the open interval, but we have said nothing about it being continuous on the closed interval, which means we can't immediately apply the mean value theorem to f on the entire interval AB. Okay, so this is problematic. However, what did we need for Lipschitz continuity? We needed for any 2 points in the domain. Okay, well, why don't we do what you were doing up above? Let's take 2 non-equal points, x and y, in the domain. Okay, you take two non-equal points in the domain, then we need to look at the difference quotient based at one of those points of the function evaluated at the other. Okay. So if I have my x and my y inside the interval, then I know that either x is less than y or y is less than x. Let's assume without loss of generality. So assume without loss of generality, x is less than y. And now I know f being differentiable on the entire interval AB, f is differentiable on the subinterval xy, which is contained in AB. Okay, but actually, because x and y are in AB here, then I also know, because f is differentiable everywhere inside AB, that f is continuous, right? Because differentiability implies continuity, right? So f is differentiable on the entire interval AB, so f is continuous even on the closed interval xy. Okay, and it's important here, right, that x is not equal to a, y is not equal to b. These really live inside, right? So I have a, I have b. X is going to be somewhere inside. Y is going to be somewhere inside. And since f is differentiable along the entire interval, it must be continuous along the entire interval. And so it will actually be continuous on the closed interval xy. And this means between these two statements, I can now apply the mean value theorem, but not to A, B, but to X, Y. So by the mean value theorem, I know that there exists some C, not between A and B, but between X and Y, such that, okay, the difference quotient, say, based at X of F evaluated at Y, is equal to the derivative of F at this point C. But what did we know about the derivative? The derivative is bounded. And so if I take absolute values, then the absolute value of f prime of c is less than or equal to m. And look what we've just done. We've reproduced the Lipschitz continuity condition. And therefore we can conclude that f is uniformly continuous, in this case on a comma b. Okay, so using the mean value theorem was a good idea here. We just need to be more careful how we're applying it. And we want to go back and make sure we use the work that we've already done. Okay, so that was a tough one. All right, let's move on to our second contestant. All right, f is a function from the closed interval ab to r such that f is continuous on the closed interval and differentiable on the open interval. Hey, that sounds familiar. That's like mean value theorem right there. Prove that if your derivative is 0 for all x in the open interval, then you are constant on the closed interval. Okay. So you said suppose f is not constant. We can try that. This implies that there exist elements c and d in AB such that, okay, a is less than or equal to c, which is less than d, which is less than or equal to b. Okay, that's true. And f of d minus f of c is not 0. All right, so if it's not constant, then you can find 2 points somewhere in the interval that are different points and have different outputs. Okay, so this is fair. Note that f is continuous on the closed interval contained in the closed interval AB, right? So yeah, right, if you know you're continuous on the entire closed interval and you take some subinterval, it will still be continuous. And it's differentiable on the subinterval as well for the same reason. Okay, so now we know it's continuous on closed CD, differentiable on open CD, so we want to apply the mean value theorem. By the mean value theorem, there exists x in c comma d such that f prime of x is in here, is equal to the difference quotient, okay, is not equal to 0. Yes, and of course this makes good sense. We knew up above f of d minus f of c is not 0. So I have a fraction whose numerator is not 0, so the fraction itself is not 0. So it might be good at this point, right, to kind of finish off the proof a bit, right? Because so what? Why is it a problem that f prime of x is not equal to 0? Well, of course, it's a contradiction. It contradicts the assumption that f prime of x is equal to 0 for all x between a and b. And here we have an x between c and d, which is, of course, inside a, b. Therefore, we have a contradiction. So we're going to say here a contradiction. Right? And of course, where does the contradiction come from? Well, we supposed f is not a constant on the closed interval AB. Okay. And if you did this, then this box here is actually at the right level. If you were finishing here, then I would want to move that box up, which you can do, by the way. It's tough when you end in display mode. This box always wants to go down. But what you can do is you can put in the command / below display skip equals negative 12 points, because the template is a 12-point font. And that will move this box up to the end of that previous line. Okay, but otherwise, it's super solid proof. Okay, let's go to number 3. Same problem. Since for all x in AB implies by mean value theorem blah. Okay, so here there's a lot going on here, but let's start with the grammatical side. This is not a sentence, right? Since for all x in AB comma, okay, so new clause. So what's going to happen implies by mean value. Yeah, this is just not what you're meaning to say. Okay, so let's start with, you want to use the mean value theorem, right? So to use the mean value theorem, we need some hypotheses, right? Namely, f is continuous on the closed interval and differentiable on the open interval. So we should restate that. Since f is continuous on the closed interval and differentiable on the open interval, by the mean value theorem, there exists an x in between a and b such that f prime of x equals this difference quotient. Okay, so that's what we could say. Fine. I don't know if it's what we want to say, but it's what we could say. Now, let's talk about this little issue. Okay, so this happens quite a bit in introductory proof writing, where you have a statement P, so here, or an expression like f prime of x, and you have some reason to believe that it is equal to some other expression Q. So in this case, the other reason is mean value theorem, right? And it's equal to this difference quotient. Fine. Then you have some reason to believe that Q is equal to something else, right? Well, no, actually, we don't. We had a reason to believe that f prime of x was equal to something. Okay, so that's actually what we want, right? So there's going to be some r here, but I actually know that it's the r that I know is directly equal to the p. Okay, and so that's actually how I want to write things down. I want to do it in a way that allows the reader to track things in a natural left to right order, right? So if I wrote down P equals Q equals R, okay, so here R is the 0, P here is the f prime of x, Q here is the difference quotient. All right. The logic is that 0, we know that's equal to f prime of x because of the hypothesis. And we know that f prime of x is equal to this difference quotient by the mean value theorem. Now, this statement here is still true, right? P does equal Q, Q does equal R, so there's nothing wrong with this mathematically. But from an expository point of view, you're causing undue stress on the reader because the reader is trying to figure out, wait, why does R equal Q? And you're forcing them to go outside of the box, right? And say, well, R is equal to Q because R is equal to P, and P is equal to Q. But in which case, why not just write it in this direction, right? R is equal to P, P is equal to Q. By transitivity, R is equal to Q. Okay, so ultimately we want this 0 equals to come first. Okay, so now let's see if you can actually use this to great effect. You say, therefore, f of b minus f of a is equal to 0. Suggests, well, that's not a word we want to use so much in math proofs. Okay. Suggests is like, okay, well, I suggest that you turn in your homework on time. All right. It's not an edict. I'm not saying it has to happen. It's just a suggestion. Okay. So we don't want to use that kind of word. You say this suggests f of x equals c for x in AB. Yeah. So I don't think this follows, right? So what I can see here, if f of b minus f of a equals 0, that tells me that f of b is equal to f of a. And a and b are two very specific points, namely they're the endpoints of the interval. So all I'm convinced of at this point is that f is constant on the boundary points, a, b. Okay, so I don't think you can make this claim. Now let's see. For the closed interval, x in AB, well, x is not a closed interval. So maybe we'll just say for x in AB, assume f of x is not a constant function. Okay, well, that directly contradicts what you said up above. Unless maybe you really meant suggests. In which case, well, you shouldn't use it anyway, but in which case you could just eliminate all this. Okay, assume f of x is not a constant function. I.e., okay, by the way, I.e. is always I period, E period, comma. F of x does not equal c. Yeah, it's a little cavalier. We probably just want to eliminate this. The function f is continuous on AB, which implies, this is our 20, right? We're not using these symbols here. Okay, this implies for all epsilon there exists delta such that if x minus a is less than delta, then f of x minus f of a is less than epsilon. Okay, since f is assumed to be non-constant, okay, so you need no space there, there exists an epsilon where f of x minus f of a is greater than epsilon. Oh, we missed this here. That should be in math mode. Okay, so the distance between f of x and f of a is greater than epsilon. Ooh, I think this is a run-on sentence now. Which implies at a, the function is not continuous, which is a contradiction. Yeah, definitely. Okay, so what are you trying to get at? You're trying to say that all the, you're trying to get that you have continuity at a, or that you're going to break continuity at a. And you're claiming that there exists some epsilon such that f of x minus f of a is greater than epsilon, but this hasn't been justified. You're just saying that there does exist it. So more explanation is going to be needed there. Okay. The way you're trying to do it, let me suggest the following approach. Instead of using the mean value theorem on just the endpoints a, b, right, use MVT on points x and y not equal to each other, right? In fact, we can even assume x is less than y, right? Some points inside the interval. Okay. And I think if you do that, you're going to find it's going to be a lot easier to, or I mean, you could even do it on the closed interval, right? That's not even a problem. But if you do that, you're going to find it's a lot easier then to conclude that f is constant on the entire interval. Because instead of just having this for f of b minus f of a, you're going to have it for f of x or f of y minus f of x. And then you're going to be able to conclude f of y equals f of x. Hey, there you go. Now you have your constancy. Okay? All right, so give this one another try. Okay, number 4. Integrability. Let f on a closed interval ab be integrable. Prove that the sum of f and g is integrable, and that the integral of the sum is the sum of the integrals. Okay. A lot of people do this upright D. I've never been a big fan of it. All right, not marking you down or anything. Just I personally think it should be dx in math mode. And the reason why is because to me dx is its own variable, right? It's an independent variable. So I put it all in math mode. But you can make an argument. Oh yeah, d should be some sort of operator. In which case, I'd still say it should be in math mode. Anyhow, let's see here. Oh, that should be in math mode. The function f is integrable on AB. Then, yeah, right. So this is a number 8 mistake. You can say since the function is integrable, it follows that. All right, so since, and you can just say f is integrable on AB. It follows that for all epsilon greater than 0, there exist partitions. Oh my goodness. P1 epsilon. Well, that's an interesting choice of notation now, isn't it? Okay. P1 epsilon, I'm curious where this is going, and P2 epsilon of AB such that the difference between the upper sums is less than epsilon. Okay, so it looks like you're talking about integrability criterion here, right? So if you are, then you should cite it. So cite integrability criterion. Okay, fine. So I can find partitions. Now, this is not at all the partition notation we used in class, right? So you probably want to adjust to match what we've been doing. Okay, fine. This, of course, when you have these sort of equations, you still need to use proper punctuation. Therefore, the upper sum yeah, this is totally not the notation we use, right? Like our notation would have been U sub F of, well, we wouldn't have used P1 epsilon either, but that's our notation, okay? Now, when you start using the other notation, it makes me a little worried about where you're getting things from, okay? Now, what did you write? U of F P1 epsilon is less than epsilon plus that, all right, comma, this is greater than, oh, this is so hard to read now. Okay, so I think you're saying these are like 4 separate things. Oy, yeah. So this definitely comes back to the don't stack equations. That's number 5. Um, this you kind of snuck around it a little bit by not totally stacking them all. But okay, so what are you trying to get? The upper sum is less than epsilon plus the lower sum. The lower sum is greater, okay, then the upper sum minus epsilon. I mean, these are all true statements. I don't know if we need all of those, but let's see. By Riemann integrability, which is kind of funny because I have never ever wrote that down. So I've been calling this Darboux integrability, right? So again, kind of worrying me here. The upper sum plus the integral. Oh, the upper sum is less than epsilon plus the. Yeah, this is just so hard to read. All right, you're just stacking so many things. Oy. It's less than this. So what is your statement that the lower sum? Are you arguing here that the lower sum is less than the integral? So I guess I can make this bigger. Yeah. Oh, there's definitely a better way to write this. Ooh. Okay, using the Mc theorem, which, okay, for those of you at home, the Mc theorem is just our way of, it stands for multiple constraint theorem. It's basically saying that when you have this situation of, oh, I have one epsilon, but then maybe I have 2 functions f and g, and I can find a delta corresponding to f and a delta corresponding to g such that something happens. Mc theorem says, well, yeah, but you can make this choice simultaneously so that you just use one delta that works for both f and g. So, there exists a partition, so you're saying a single partition, and f plus g being integrable means that u of f plus g equals, I don't know what this means. I don't know what you're talking about here, because when we write down u of f plus g, that means there needs to be a partition now, right? This is the upper sum, and of course it was supposed to be something like u f plus g of a partition. Yeah. So I think you're getting this from somewhere. All right, that's what I'm looking at and seeing. And in which case, man, you got to write your own. Okay, so it's going to be hard for me to judge what's going on because I don't know what this notation means. I'll just make a couple little comments. You'll notice here you have your parentheses that seem very tiny next to the integrals. So consider using /left and /right. Before your opening and closing parentheses. That will resize your parentheses to match the content that's on the inside. Likely that's going to be useful, on this line as well. And then you can do the same thing with your absolute values, right? And these parentheses here. Okay, so why don't you resubmit this one, and then I can make the notation jive with what we've actually been doing, right? Because I can't read what you're doing. All right, number 5. All right, so we have a function from closed interval AB, which is integrable on AB. U is some differentiable function from some open interval CD to AB. So we can compose. I can apply U. Now I go into AB, and now I can apply F. Prove that. Okay. Actually, I'm kind of interested in how you're getting into this central mode. Are you using a begin center, or are you going into using an equation environment? Because if you use the equation environment, I would have expected this integral to be a lot bigger, which would really enhance the readability of this. If you're using a center environment, don't use the equation environment here. Okay, let f be integrable. Okay, so we don't want to do this, right? So what are we doing? We are repeating the hypotheses, okay? And that's number 15, okay? We don't do that. You could say since it's integrable, but we're not going to say let it be integrable. You don't let that which is already true, and we just did it, right? It was just let. And the function, well, I mean, what you could do is just say let f be defined by, right? So you'd cut all this stuff. So let f from here be defined by f of x equals that. Okay, you've chosen to number it, which is fine if we use it. So I do see a 1, so that's pretty reasonable. Let u be different, and again, we're not letting that which we've already assumed to be true. So you're saying by the intermediate value property, C and D are in AB. Oh no. Oh no. We C and D have nothing to do with AB. Yeah, the AB could be over here, and CD could be over here, right? Like that. Well, I'm not drawing that quite well, am I? Right? CD could be some interval over to the right or to the left. Like it doesn't matter. Point is, they don't have to have anything to do with each other. You're saying then x lies between u of c and u of d. I don't know what x is. And there's x in AB such that u of x equals x. Oh, you're saying that u has a fixed point. Well, I mean, that's probably not true. I can think of easily differentiable functions that don't fix anything. You know, for example, maybe u of x equals 2x on the interval 1 to 2. Like nothing gets fixed, every number gets doubled. So I'm not really sure where you're going with this. You say now substituting 2, this u of x equals x, into equation 1, we obtain that f of u of x equals the integral. Okay, I mean, you don't need equation 2, right? This is just, you could just jump right to this. I'm not sure you need any of this stuff, right? So yeah, so if you just say, okay, f of x is equal to that, we know that the range of u lies in AB, which is certainly in the domain now of f. So you can certainly write f of u of x equals this. Yeah, I think you can just jump right to this line, right? That's fine. Okay, by using ftalk1, we just say by ftalk1, which, by the way, for those of you at home, that means the first fundamental theorem of calculus. We have this derivative. Okay, so actually, there's something that you actually need to check. All right, and there was actually a typo in the problem. Okay, so in order to use the first fundamental theorem of calculus in the way that you're expecting, we actually need for f to be continuous. All right, as we've written everything down, this function, I mean, you can always define f, but if you want it to actually be differentiable, then you need that little f was continuous. Okay, at least that's what, that was our version in class. So that's actually something you should be aware of, and then you need to cite that, right? So since f is continuous, we can apply ftalk1, right? And so we get that this derivative is equal to this derivative. Fine. Good. Now you're saying by the chain rule, we have the derivative fu of x equals f prime of u of x times u prime of x, fine, which is equal to, okay, and Yeah, I mean, okay, let's go back up a second. Like, you're saying by f-talk1 we have that this derivative equals that, but that's not f-talk1. This is just saying I have two things that are equal and I apply the derivative of both sides and they're still equal. That's not what f-talk1 would say. F-talk1 actually tells you how to take the derivative, right? So we know that the derivative, right, what does f-talk1 imply? This implies, assuming f is continuous, little f is continuous, implies that the derivative of big F is equal to little f. Yep. And that's what you're using when you get to this step right here. Right? So when you're connecting these two up. So this is where you're actually using f-talk1. Okay, so that needs to be closer to it. Okay, and so then, yeah, this is just cleaning it up. Okay, so that's fine. So you have the right idea. You have way too much going on. You have unnecessary things, and then you need to connect f-talk to what it's actually doing, right? It's not. This is not f-talk1. Okay. In fact, it doesn't seem that you really even need this line at all. Okay, let's go to our sixth and final one. All right, we're back to proving that the sum of integrable functions is integrable. Okay, yeah, again, same question as I had on the other one. Like, are you in center mode or equation mode? Because really, these things should be bigger if you're in equation mode. Right. Oh, what's going on here? I don't know why there's a colon at the beginning. Get rid of that. Since f and g are integrable for all epsilon greater than 0. Okay. I think maybe you're wanting a comma or something. Since f and g are integrable for all epsilon greater than 0, let P be a partition such that, well, hey, you all are just ignoring my notation, aren't you? Okay, so our notation for upper sums was, if you want to use a capital P, like, I'm not like super thrilled because again, it's not the notation we're using, but at least use the same notation that we're using in class. Okay, so the way you need to say this is for all epsilon greater than 0, there exists a partition. So we'll say there exists a partition P of AB, or maybe you even use the notation for partitions we came up with, right? You could say, right? Or don't use this symbol, of course, I'm just abbreviating, but there exists. Okay, well, I'm just going to use the notation X in PAB, right? So this was our set of partitions, right? Such that, okay, well, it sounds to me like you're using the integrability criterion. So again, we want to cite the integrability criterion. Okay, such that the difference between the upper and lower sums is bounded. Okay, well, why is it? So why does a single partition P work for both F and G? For both F and G, right? I mean, I might say, well, I have some partition that works for F and I have some partition that works for G. Now, the answer to that is going to be that, well, probably you're not starting off with the same partition, right? Maybe you have some PF and some PG, but you can take a common refinement of those partitions. And because we have properties of upper sums and lower sums, when we take refinements, upper sums are going to get smaller, lower sums are going to get bigger, so their difference is going to get even smaller. And so there's an argument to be made here, but essentially you make that argument once and then it falls under the McTheorem situation. You say, cool, I can always find a single partition that will work along with the integrability criterion for two functions at once. But there's an argument to be made there. Okay, you say it follows that the difference between the upper sums of F plus G is bounded by these differences. Yeah, this is totally unjustified, right? So, yeah, you're gonna need to explain this. Like, it's not obvious to me. How are you getting from one upper sum to a sum of upper sums? All right. You haven't written anything down to justify that. Now, let's say this was true, then, okay, fine. You could break this. Oh, okay. So you want to use an aligned environment. So learn the align or align star environment. That'll help you get all these things lined up nicely, because this is just an abomination at the moment. It's weird. It looks like you're leaving math mode somehow. Like, I have no idea even what you're doing. I'd love to see your code, but this spacing here is really bad. That's how I know something's going on. Like, you're leaving math mode. Maybe you're going into center. Are you doing like a begin center, end center on every line? Oh, and then leaving and not like leaving math mode, going back into math mode? That would be terrible. Okay, you need to finish with a period, by the way. Furthermore, okay, probably don't need to start a new paragraph. This integral is less than or equal to the upper sum is less than or equal to the sum. Yeah, again, this isn't justified. Is less than this plus 2 epsilon. And okay, also notation-wise, you notice you're missing your dx's. Yeah, same thing. All the dx's are missing over here as well. Okay. Yeah, adding both of the inequalities. Good, the dx's are back. Okay, so that should be okay at the end. This thing wants to go up. See the second problem here to see how the command for doing that. Okay, yeah, so there's a lot of unjustified stuff here, right? And you got to take care of that, and then you can resubmit. Okay, well, that is all 6. We will see you next time on everybody's favorite video series, Watch Your Professor Grade.